let us do them. Maybe I will write applications of
we discussed about the similarity between quadrilaterals and
yes, right. And then I had given some questions. So let me first mention the topic. And Ishani, you were not there, but don't worry. You will get to it. It is not very hard, and I have done a bit of some similarity. Let's see. We'll just solve the problems. Yeah. So applications of similarity. But here, obviously, it's not similarity of triangles. That's very easy. Similarity, just application. So, so let me first define what I mean by similarity, because we should have a clear-cut definition. So we did discuss things. So let us say that there is one quadrilateral. There is another quadrilateral. So quadrilateral. A1, so we say that ABCD is similar to A1, B1, C1, B1. Okay. So Aparna, do you remember the definition?
so the definition of similarity, or what are the necessary conditions?
Anything, maybe you say the definition, what you think is the definition, because yeah.
Sir, I think we were discussing that the only thing that the angles are equal is not enough to say that the quadrilaterals will be similar.
Right. But then what should be the definition? So let me, yeah. So what do we want the definition to be? We want it to be that this equals BC by B1 C1, right? And but we have to mention all of them. CD by B1 B1 and DA by B1 A1. But this thing we want to say is not enough. Now, why do we want to say it's not enough? Well, you can take the definition to be anything, but what we want it to be is that, I mean, that one is like a scaled version of the other, right? So we also want that the angles should be same, right? Now, the point is that this thing by itself, does it, if you have this, right, then does it mean that the angles, that the corresponding angles are same? If the ratio of the sides are given to be the same, does it mean that corresponding angles are same? Well, not at all, right? Because even if you just take one, I mean, even if you take the sides to be equal, right? You take a square and you take a rhombus, right? I mean, even if you take the sides are the same, forget about the ratios. Here, the exact sides are same. All the lengths are same, and all the corresponding ratios, they are all one. Still, the angles are not the same, right? So, by no means is this going to imply that the angles are same. So, we have to put that in the condition. Is it making sense, Shanna?
Yes, sir.
Right? You see, so only this is the thing with quadrilaterals, and you know, and I'm saying that we know that this doesn't happen in triangles. In triangles, just the ratios being same does imply that. So there is a sense of rigidity and in triangles which is lost in quadrilaterals. So it doesn't imply, and that is why we must put something more, because we want all sides and all angles to be sides, corresponding sides, same ratio, corresponding angles to be same. That's certainly what we would want from similarity, right? So plus, now let me just mention one thing at a time and see if it's enough to give us more. what if I say that DAB is equal to B1, A1, B? Let's say I just give this one extra bit of information. My question is, does this force the other angles to be the same? Does it imply the other angle? Let's say that this was 75. Okay, maybe I'll not put the number there. You people are smart enough. Okay, I think we have discussed enough things. What can we say about ABC and A1, B1, C1? Can we see anything? Or about
Sir, we can divide the quadrilateral into two triangles to prove it.
okay. So you are saying that you're saying the answer is yes, in the sense that all the other angles will be same in the corresponding
Yes.
sense. Good. So I don't want to. I'm not looking to prove. I understand that the proof you guys do. So yeah, Aparna, you also agree with it? All this last. Just
Yes,
one.
I did
Yeah.
the class.
Yes. Right. Just one bit of information gives the rest. So that is plus this plus one. So maybe I will. So now, how should the definition be? Wait. Okay. I'll do one thing. Once. Yes. Now, so I should say that plus some corresponding angle is. Now we can frame this in several ways, but let's not go into all that. They will all be easy. No point doing too many easy things. Corresponding and some corresponding angle is same. Okay. So that's it. Now the question. Aparna, do you remember the question? Some I don't know. Who noted it down? Okay. Okay, no problem. So let us see. So
Sir, I think we discussed something else like in a circle we had a triangle and
yes,
then
yeah,
we
yes, that is fine. But the now I want to come to the homework. We discussed some other things also. I know, like when we have polygon and so, but just about this quadrilateral question. So if you don't know problem, if you don't remember, so let us say that we had this quadrilateral, right? This, and let's say they are similar. So I've mentioned this. Now let's say that this is 2 and this is 1. Keeping it. Okay. Now if the quadrilaterals are similar, now if BD is equal to 3, yeah, find, okay, I don't know. Now it looks too simple. Somehow. Find B1D. So the quadrilaterals are similar. Okay, I don't know about that. BD is equal to 3. What is B1D? Sorry. So right now we have very clearly discussed the definition of similarity. So it should not be difficult. Last time we had sort of a strange way towards it. So now it should be very straightforward.
Sir, all the sides are in the ratio 1:2.
That's right. So this would be, maybe I'll say 2:1 because I'm writing this on. Yeah, so we know about sides. So similar means that one is a scaled version of the other. Okay, so the angles are also same. Okay, also we have put that in the definition, so it's not controversial. I mean, just it will just be the most. It will be the first thing that comes to your mind, sort of. It's just a scaled version of the other, right? One is a scaled version of the other.
Shouldn't it be 1.5?
Yes, right. So can you give an explanation?
The ratio remains the same. So all the angles we know are equal, the corresponding angles. So the ratio of the diagonals will also remain the same.
But you have to say more because it's maybe it's obvious to all of us, right, that the ratio of the diagonals is the same. But still, how do we arrive at that from what is given? That is a logical thing that should be said logically speaking. Why is the ratio of, so why is this 2? Come on.
Sir, when we join BD and B dash D dash,
Uh-huh. Right.
sir, then can we say that BD will be greater than, less than 2 times AD plus AB?
BD will be greater than 2 times
AB plus AD.
AB plus CD.
Sir, AB
No.
plus AD. AD.
AB plus AD. No, no, no. It has to do with the comparison between these two, right? Because nothing is given about the triangle. Nothing is given about the a quadrilateral itself, but it's a comparison. Come on. So these two are similar triangles, right? We know that this angle is equal to this angle, right? And it is written here that AD by A1 D1 is equal to BC by B1 C, right? So aren't these two triangles similar? Right? Common angle is equal and the sides are in the ratio. Ratio of the sides is proportional. So it is similar, right? That's all. That is all, right? So you have to, so if you feel that BD is equal to B1 D1, now in order to say that, right, you have to say it from some theorem or say it using something basic. So you have to see it as part of some triangle. That's your only way, right? It is easy, right? Okay, no problem. So it means that you didn't try it. Others are also not here. I don't know if they would have tried it. But anyway, so we did it. So that's the point. We have done it now. And then now I don't want to go into variations of this because it will be similar. It's easy. So leave it. Why did I give any other question upon? You were saying something about cyclic quadrilaterals.
Sir, as much as I remember, there was a circle and there was a triangle, and you were asking that when the base angles are changed, then how do we prove that the other vertices also will lie on the circumference?
Right, right. Yeah. Let's come to that. That is a very, very important result. Okay. So, yeah. So, yes. Let us take a triangle. That's right. And then we have a arbitrary. So through these, we will learn all these basic things about circle geometry. Yeah. And then this came from some discussion, but we are not going into that. this problem. This is ABC. Pay attention. This angle is here. Now we make, keeping the base the same, I make another triangle. Okay, let's say just any other random triangle. Nothing is given except the only thing that is given is that this angle is. Why does this become? Am I writing in the wrong way? Okay. This is, let's say, D. We want to show, and this would be slightly a different kind of question than what you would have seen so far, like a different kind, in the sense, show that D is on the circle.
So is angle D equal to angle A?
Angle D, angle BDC is that.
Yes, sir.
Yes, yes. Otherwise, why would it be on the circle? Otherwise, there's nothing given. Yes, yes, yes. That this marking is how we understand it as like that. But let me write. So, Aparna, did you try this? Were you able to show this?
Sir, I actually knew this theorem that in a cyclic quadrilateral the angles subtended by the chords are equal.
Okay. So let us see how this is related with this.
So if you join AD, then you can say that it has to be a cyclic quadrilateral because BAC is equal to BDC.
Okay. Let's come to the first statement. First statement you said is that if D is on the circle, then BAC is equal to BDC. Yeah, right?
Yes, sir.
Right. So, Ishana, are you aware of this result? If this point is on the circle, so you can forget about this D for a second. Some other X, right? Then these two angles have to be equal. Right? So you take circle like this, and then we go like this. Then these two angles will be equal. Ishana, do you know this result?
No, I don't think so, sir.
No. Okay. So Aparna, then you have to prove it. First, let's try to prove it. Or maybe just let's give ourselves a little bit hint, maybe, even if you don't know. These two angles are going to be the same. So the hint is, and this is a homework, is this is a very standard. If you just see any NCRT, also the circle geometry, maybe class 11 or something will be there. I don't know now. They may have updated it. I don't know. The point is to compare it with the angle at the center. And you will see it is not difficult. So let's erase this thing. This is the center of the circle. Like you have to use the fact that this is the 3 points are on a circle. So you draw the center. Now, do you see a lot of isosceles triangles? Yes. This is the radius, right? The black ones. So these are isosceles triangles, right? So now you can just do some angle business, right? So if this is x, right, this is y, right, then then this is also x. Is it visible? And this is also y, right? Now again do some angle business, right? You know that this is z, this is z. I mean, sorry, you write it as z, right? And you can relate these numbers, right? And then you do all that, and finally you will be able to show, do that work, and finally you will be able to show. So this is homework. Is that this angle BOC turns out to be 2 times x plus y, which is the angle BAC. Okay, it's 2 times BAC. Fine, it's also believable, right? Is it believable? And you can just do it. Please work this out. This is a homework. Work it. Now we are done, right? Because this angle at the center is 2 times this, and so this is a constant angle. Any other angle you take, it has to be half of this, right? If you take it on the circle. So is it fine?
Yes.
So now you take
Yes.
that as a home. So this here, but it's complete. But we are interested in something a little more. If this point x was on the circle, then the angles would have been same. But I am saying the opposite of it. If the angle is same, then it is on the circle. I am asking for the converse of the statement. Right? If this angle is equal, then this point is on the circle. And that is the power of this result, right? That even if the circle was not there, right, you would know that these 4 points will be on a circle, right? If you prove this result, if you prove this, right, then you say, okay, BAC are on a circle, D angle is equal to the A angle, so it has to also be on a circle. So all the 4 points, it has to also be on the same circle, right? So all the 4 points are on a circle. And this will allow you to know that these 4 points are on a circle. That's pretty fantastic, right? It's quite a lot, right? You get. That's why the result is important. But the proof you may little strange. So what do? We know that if this D was on the circle, then the angle would be same. So we extend it on. Now look at this method very carefully and try to understand. This method is used every time. Whenever a proof statement like this is used, in a sense, used very often. I will extend this line to join this. Question is, what can you say about this angle? What can we say about BEC? So remember that E is on the circle. So what can we say about BEC? So now the D is not playing a role. Just focus on this E. The D is not, the D is not even there now for a second. What can you say about BEC?
So that it would be equal to BAC.
Right? So it is equal to BAC. That's perfect. Yeah? So it is equal to BAC. Yeah. Fine. Now these two angles are same, right? BDC is equal to BEC. Now the A is not important. Right? You can see BDC is equal to BEC. Then shouldn't D and E be the same points?
Yes.
Right?
Yes.
Now, right. Obviously, one can prove it, but fine. I mean, we assume this much, that if you make two angles like this, they cannot be the same. Right. That also needs a proof, to be honest, from the one of the postulates, Euclid's postulates, the unique perpendicular, and so on. But fine, we understand this. Good. So then we know that D and E are the same point, and so D has to be on. See the method very carefully, right? I've extended the D, to its closest point, the point that it should be. You could have extended it another way also, it would have given the same result. You would have proved the T there. So this is a good result. All right. This is maybe we should do an application of this, right? Just to
Sir,
get
can you explain again how BEC is equal to BAC?
BEC is equal to BAC. Yes, look at this picture. And so the result we just did, right? That if you have a circle, and if you have two angles like this, look at the nature of these two, right? They are the same base. So we said now that these two angles have to be equal, right?
Yes.
Right? And that's the situation here, right? We have a common base, and these two are on the same circle, so their angle has to be same.
Okay.
Right. So the D is not important in that case. So we have. So this is a very nice result. This tells you that, I mean, this tells you that if just you are given just some crisscross, it doesn't even have to be like just some, like this. And if these two are given to be equal, then you know that there is a quadrilateral that passes through all of them. I mean, there is a circle that passes through all four of them. That's what we have proved, right? So you take a circle passing through the triangle, and then it has to pass. That point has to also be on the side. Okay. Let's prove another theorem using this theorem, which is also a very standard theorem. First, let's prove the, maybe one can say, the easier direction. We have this, just another arbitrary quadrilateral. See, the kind of results you're proving, we're not assuming anything other than they are like cyclic, or or we are proving that they are cyclic. So I want you to show that this angle is equal to this angle. This is also a standard theorem, but we will prove it using what things we have already done. So just a hint is that we will be using this result because circle is there. Sorry, I'm talking too much, but what I want to say is that we'll be using this. also pretty nice result, right? This interior angle is equal to opposite exterior angle. Let us see. Okay? We have to create this situation, otherwise, how will we go forward? Right? We have to use this. It's like the only thing we sort of know about angles. So, if we want to use this, we should create that situation. So we, join this. Maybe label it. But then you see this is not going to be enough, right? We should join this also. Okay. So you see this is my x and this is my y. I'm just breaking it up. Now use that theorem. So you want to show that this is also dCz is plus 1. Right? Okay. So what will BDC be?
Sir, X.
Right? X by the
Yes.
result. Yeah. Now, so this is okay. So I'm just saying this because just what is CBD?
Sir, Y.
Right. So this is y. Now again, that's the same thing, right? CD is fixed and the A is moving on the circle. So it comes to B, but the angle will not change. It's the same thing, right? This angle will be equal to this angle. And so it has all these nice consequences, all the things. Okay? Then are we done, right? Then this is x plus y. We all know that, right? Triangle, then this is x plus y. And it's very, very simple. There is nothing in it. So, so now the meeting is going to end. Now we are going to prove the converse. Okay? So if this yeah, so maybe just join on the other side, then we'll prove the converse. Okay? Ending